We talked about covalent bonds, and now we're going to, we talked about ionic bonds, now we're going to talk about covalent bonds. Lewis structures for covalent bonds show the atoms next to each other and dots in between where the electrons are shared. The atoms are going to share electrons so that they can all get an octet of electrons, or for hydrogen, he's just trying to get a duet. So let's look at water and molecular chlorine and look at the Lewis structures for those. So water is H2O. So we've got oxygen, and we've got, how many valence electrons does oxygen have?
6.
6. So there's 6 valence electrons. And then we've got 2 hydrogens, so I'll put one over here and one over here. And how many valence electrons does hydrogen have? 1. So these are both nonmetals. And so there's not going to be a transfer of electrons. They're going to share electrons to get 8. So hydrogen wants 1 more electron. Oxygen's not willing to give it to him, but I'll share with you. And so what I'm going to do is just connect those 2 dots. Oxygen's sharing this electron with hydrogen. Hydrogen is sharing that electron with oxygen. When you share something, the thing belongs to both of you. So hydrogen looks at electrons and says, I have 2 electrons now. I'm happy. The oxygen looks at these 2 electrons and says, I have 2, 4, 6, 7. I'm happier, but I haven't gotten to 8 yet. So oxygen says to this hydrogen, how about we share electrons and then we can make each other happy? And they do that. Okay? So when hydrogen counts up his electrons, he's got 2. Hydrogen's a little guy. 2 is good enough for him. And the hydrogen over here, 2 electrons. When oxygen counts her electrons, she says, I've got 8. Okay? The sharing of electrons counts for both. My husband and I have 6 children. If you ask him how many children he has, he'll say 6. If you ask me how many children I have, I'll say I have 6 children. How many children live in our house? 6, not 12. Thank goodness. Question?
So when we're doing this on mastering chemistry, for the homework part, will we draw the lines too? Or like how would it show up as an answer?
It kind of depends on the question. But usually we represent bonds as lines.
Okay.
What I'm doing is I'm showing these bonds. This is a single covalent bond. I'm showing this as 2 dots connected by a line to help reinforce to you that the bond is 2 electrons. And we'll sort of transition into using lines instead of dots. Yes?
So then could it also be written like the O with the 8 electrons on the sides, and then with the H just attached to the 2 dots on each side?
The normal way it would be like this. That's the grown-up version. Okay. So you show lone pairs or lone electrons, non-bonding electrons as dots, and the bonds are generally shown as a line. Here I'm showing you how this comes about. So we have different types of electron pairs here. We have bonding pairs and we have lone pairs. The bonding pairs are the electrons that form the bonds that are being shared between the different atoms. And so these guys right here, those are being shared. Those are bonding electrons. It's a bonding pair, and this is a bonding pair. So bonding pairs in red, and we'll do lone pairs in green. Darn. Lone pairs in green. So these guys up here and these guys down there, they are not involved in a bond. You could say it's a pair of electrons that's alone. It's not shared between. So it's important to be able to look at a Lewis structure and identify how many bonding pairs, how many lone pairs, because that's going to be important later. I just, made a big old mess there. Okay, let's look at chlorine. We'll make chlorine be orange. So molecular chlorine, there are 2 chlorine atoms. And how many valence electrons do they each have? 7. 1, 2, 3, 4, 5, 6, 7. So what I'm doing there is I'm drawing the Lewis structures next to each other. And then we're going to look at this and see how could these guys share electrons so they could each have an octet. Well, it's pretty obvious. We'll just share. They each have 1 unpaired electron, and so they'll share those. And now each chlorine says, I've got 8. And this one says, I've got 8. And everybody's happy.
And the grown-up version would be the dots on the outside and just a line in the middle.
Yeah, the grown-up version would be this way. So in this molecule, how many bonding pairs are there? 1. How many lone pairs are there? There's 6 lone pairs. 1, 2, 3, 4, 5, 6. Okay, yes?
If the bottom one is the grown-up version, what's the first one?
This is the learning how to do it version.
Oh, okay.
It's the baby version? No, not really. It's really the baby version, right? I don't want to be offensive. But, when you're learning to do something, right, you don't do it as well originally. I remember my second son, we were at a restaurant, and he's pointing over at the cashier station and saying, "Dollar biller, dollar biller." He meant the cash register. Did I know what he meant? Yes. If an adult called it that, though, we'd laugh at them, right? So what I'm showing you here is to help you understand how we put them together, how they work. And then today, we're going to learn how to do it like this. This is all, nice and pretty and fancy. Okay? Any other questions? Right, yeah. So those were single bonds. A single bond is where a single pair of electrons is shared. We can also have double and triple bonds. So let's look at what happens with oxygen, molecular oxygen. So each oxygen has 6 valence electrons, right? So let's draw an oxygen here and an oxygen here. And this one has 6 valence electrons, and this one has 6 valence electrons. Well, if we share 1 pair, if each oxygen shares 1 electron, do they have an octet? No. What could they do? They could share 2 electrons each. And that's called a double bond, because 2 pairs of electrons are shared. So that's a very awkward way to write it. So normally we'd write it like this. The 2 lines represent a double bond. Each line represents 2 electrons connected. That's why I did connect the dots. And then the lone pairs. And you can put the lone pairs on the bottom and the top or whatever, but stay with top, bottom, right, and left. So this is the Lewis structure for oxygen. How many bonding pairs? 2. How many lone pairs? 4. 1, 2, 3, 4. Any questions? Oxygen is a molecular element because when 2 oxygen molecules get together and form a double bond, they are more stable. Their potential energy is lower. Chlorine is a molecular element because it shares 1 electron with another chlorine atom and becomes a molecule, and it's more stable. Let's look at nitrogen. Is nitrogen a diatomic element?
Yes.
Yes, it is. How many valence electrons does each nitrogen have? 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I'm looking ahead to what I'm going to do, and so I'm drawing the dots in a particular way. Well, what's going to happen here? Here's a clue, triple bond. They each share 3 electrons with the other nitrogen atom. This nitrogen atom counts all of the shared electrons as belonging to him. So 2, 4, 6, 8. He's happy. 8 electrons. This nitrogen, same situation. 2, 4, 6, 8. And so we can draw that a little nicer over here. There's 3 lines, and then there's a lone pair on each side. So my husband and I have a triple bond of children, right? 6 children. Any questions? Pardon me? No, there's no lone pairs. Well, maybe those could be 2 of the cats and the dog that's still alive and the dog that's dead. I don't know. Analogies can be taken too far.
2 colons, perhaps.
2 colons?
Yeah. You know, just talk about another map.
Well, I know, but people have colons too.
Yeah, I was going to say that.
Okay, we're going to move on now. That took a turn for the worse. Okay, so covalent bonding, one of the purposes of bonding models is to predict and explain what we actually observe. So the Lewis model can help us to predict the stability of molecules. And so we're going to look at water, which we know to be stable, and we're going to look at H3O, which is unstable. So now that we're getting a little better at this, so we've already done the Lewis structure for water, and so I'm not going to go through how we did it. I'm just going to basically copy it in here. So that's the Lewis structure or Lewis model for water. And we look at this and we see that the hydrogen has 2 electrons, this other hydrogen has 2 electrons, the oxygen has 8 electrons. Everyone's happy and stable. So we predict, yeah, water is a stable molecule. And sure enough, it is. What about H3O? Well, what do we have to do to put another hydrogen on here? So here comes another hydrogen, and he wants to get in on the action. It's like, hey, oxygen, share an electron with me. The oxygen's not real happy about this, but if he goes ahead and does it, he shares one of those electrons with the hydrogen. This hydrogen's happy. It has 2 electrons, these shared electrons, but what happened to the oxygen now? It's got 9. 9 is not 8, and sometimes more is not better. 8 is the magic number. They want to have 8. So we look at this and we say, this violates the octet rule. This is probably not stable, and it isn't. We don't find H3O. It just doesn't form. What about H3O+? This is the hydronium ion. Well, we've got H3O here. What do we need to do to make it H3O+?
Take away electron.
Take away an electron. So let's take away an electron. That makes it have a charge, so we should put brackets around it and put the charge on the outside. Would this be a stable molecule?
Mm-hmm.
Yeah, because now the oxygen has 8 electrons again. Each of the hydrogens has 2. Everybody's happy. The hydronium ion is a stable ion. How about H2O2? Well, if we put H and O and O and H. And here's the 6 electrons for the oxygens. And there's 1 for each hydrogen. We can see that if the hydrogen shares 1 with oxygen and this oxygen shares 1 with the next one, it's like they're holding hands almost. Does that satisfy the octet rule? Yeah. Each of the oxygens has 8, and the hydrogens have 6. So 6, where did that come from? 2. They have 2. This is a stable molecule. Now, someone asked a question yesterday, and I thought it was a really good one, because you probably learned about the hydronium ion in a previous chemistry class. And it's a little confusing to students because we often use hydronium and hydrogen ion interchangeably, and that's a little confusing why we do that. So I'll just explain that. So a hydrogen ion, H+, how many electrons does it have? None. It has no electrons. So it's just the nucleus. So it's just a bare nucleus, and the nucleus for a hydrogen ion is 1 proton. This is a single proton just out there, right? That's not going to be real stable. It's a little bit like a newborn baby, right? Do you see newborn babies out on the street by themselves? No. Hopefully not. You see them being held, being carried by larger people, right? Or in a carriage or something. So this hydrogen ion, not really very happy. And so I'm going to draw this water sideways. So all of these acidic reactions are happening in aqueous solution, and so wherever there's this hydrogen ion from an acid, there's a lot of water molecules. This hydrogen is not happy. He would really like to have 2 electrons, and so he sees this water molecule, and he says, hey, I see you have a lone pair here. Could you share that with me, please? And the water's like, sure, I could do that. And so when the hydrogen ion rides on a water molecule, I think of it as riding piggyback or being held by the water molecule, then we get this hydronium ion. This oxygen is still okay. He's still got 8 electrons, and each of these hydrogens has 2, but now this hydrogen ion is much more stable because he has 2 valence electrons. And so we never really see hydrogen ions just loose in solution. As soon as a hydrogen ion is formed, it immediately attaches to a water molecule. The reason that we don't always write H3O+, why we sometimes write H+, is it just makes all the equations much simpler. But we just understand that wherever there's H+, it's actually riding on a water molecule. Any questions?
So can you get H4O2?
Can you get H4O2? Well, let's look and see.
Not O2, like, also,
H4O.
yeah.
Well, let's look and see what would happen. So here's H. Oops, having trouble with my markers. So if we stick another H on there, and they share, is that going to be stable? No. What if we made it a 2+ charge? Lewis model says that might be okay. Now, have you ever heard of H4O2+? Me neither. That's not stable. The Lewis model is not perfect. It doesn't predict everything. Yeah. Any other questions?
See how you have the ion, just H+,
Mm-hmm.
and you said it bonds to water molecule?
Mm-hmm.
What does that look like? The Lewis dot structure. Is there a way to represent that with Lewis dot structure?
Right here.
That's
That's what this is.
H+.
Oh, you mean to represent H+ as a Lewis structure? That is the representation. There are no electrons, so there's no dots.
Now, why are there 3 of the H's in H2O Lewis structure?
This is the Lewis structure for H3O+.
Okay.
So I took H2O and I added a hydrogen on it.
Okay.
I made it the H+,
Okay.
H3O+.
And then the one on the
This
bottom
is
right.
H2O. This is H2O.
Okay.
That's water. So these two get together and form that. Any other questions? Covalent compounds have discrete molecules, and the Lewis theory helps us understand that. In an ionic compound, you have positive and negative charges, and they are attracted to each other in all dimensions. In a covalent bond, those electrons are shared between 2 particular atoms, so we say that bond is directional. Because the bonds are highly directional, we have individual molecules. You might remember a question on an experiment post-lab. Can can you find a molecular formula for an ionic compound? No, because ionic compounds don't have molecules. They just have repeating patterns, alternating cations and anions. But in covalent compounds, you have these discrete bonds. The water molecule, you have two hydrogens, and they're bonded to the oxygen, and there's no covalent bonds between those atoms and another water molecule. Now, why don't the water molecules just fly apart from each other? How can we even have liquid water? We'll learn about that later. Those are called intermolecular forces, forces of attraction between molecules. But they're not nearly as strong as the actual bonds. And so because we only have weak forces between the individual molecules, covalent compounds, molecular compounds, tend to have lower melting points. They're not as predictable as the ionic compounds, but they tend to have much lower melting points.